Welcome to our fourth video on stoichiometry, in which we look today at limiting reactants and excess reactants. A limiting reactant is a reactant that gets used up first, or we say depleted, in a chemical reaction. Often scientists will make one of the expensive reactants the reactant that gets used up first so that we can save money that way. The limiting reactant is the amount of product that limits the amount of product that is formed because the reaction stops when the reactant is gone, and it also limits how much of the excess reactant is used up. Remember in our recent lab in which we burned ethyl alcohol in the watch glass, the ethyl alcohol got used up. It was the limiting reactant, even though there was still plenty of oxygen around. The excess reactant is the other reactant or other reactants, and those are the reactants that are left over when the reaction stops. And if you remember back to our very first reaction in the year, which we had the two different situations with aluminum and the copper 2 chloride, in one of the situations the aluminum was used up and the copper 2 chloride blue solution remained, and in the other situation the copper 2 chloride blue solution was used up and the aluminum remained. So the important thing in this section now is going to be learning how to identify which of the reactants is going to be limiting. For my favorite reaction, nitrogen gas plus 3 hydrogen gas yield to ammonia gas, we're going to first look at what would happen if we didn't have a limiting reactant. If we had 1 mole of nitrogen and 3 moles of hydrogen, then both of them would get used up. In other words, nothing would be limiting. So the stoichiometric coefficients here are going to show us the relative amounts of each of the reactants that get used during the reaction. But if the mole amounts are different from those coefficients, what we have to do is calculate something that's called the equivalent, or the equivalence for each one of the reactants. So for example, if I have 1 mole of nitrogen and 2 moles of hydrogen, what I'm going to do is I'm going to take the actual amount of moles, the moles that are given to me in the equation or in the problem. So 2 moles of nitrogen and 2 moles of hydrogen. And I'm going to divide those actual moles by the coefficient moles, the implied 1 here and the 3 in the hydrogen, to get what we call the equivalence. Let me show you what that looks like. For the nitrogen, I'm going to take my 1 mole of nitrogen that I was given. So in this case, the 1 happens to come here. I know it's a little confusing because there's 2 1s there, but you'll see how this works a little bit differently in a moment. And then I'm going to take the 1 from the coefficient, and I'm going to put that down here. And 1 divided by 1 is 1, and these numbers are going to be unitless. So no units on these numbers. For hydrogen, I'm going to do the same thing. Now in this case, the hydrogen I was given 2 moles of hydrogen, which I'm going to put up here, and I have 3 moles of hydrogen as my stoichiometric coefficient, and so 2 out of 3 means I only have 0.67 equivalents of hydrogen. So as you can see, 0.67 is less than 1, and because there are fewer equivalents of hydrogen, so we have fewer equivalents of hydrogen, we have hydrogen as the limiting reactant. A slightly harder problem, only because we've thrown some non-integer numbers at you here. If we have 2.3 moles of nitrogen and 7.6 moles of hydrogen, which reactants is limiting? Of course, we're still using that same reaction. So what we're going to do is take our 2.3 moles of the nitrogen gas here and divide that by the 1 mole from the balanced chemical equation to get an equivalence of 2.3. For the hydrogen, we're going to do the same thing. Take our 7.6 moles and divide by 3, and we get 2.5 equivalents. And now in this case, because the 2.3 is lower, I'm going to identify nitrogen as the limiting reactant because it's going to get used up first during this reaction. So far so good, I hope. Now as we move forward, we're going to get things a little more detailed, I should say. Usually we work in mass, and in our lab coming up on this concept, we're going to be dealing with masses of reactants because, of course, our balances give us mass and not moles. So for the same reaction now, we're going to look at starting with 20 grams of nitrogen and 10 grams of hydrogen. Don't assume automatically that the smallest amount is going to be the limiting reactant, because that smallest amount in this case is going to depend on both the mass, the molar mass, as you'll see in a moment, and on the coefficients. So the first thing we have to do is to determine the number of moles of each of the reactants. So we're going to go back to our molar mass, and we're going to take each of the grams and divide by the molar mass of the reactant, or multiply by 1 over the molar mass. Keep our good dimensional analysis. Of course, the grams of the hydrogen cancel with the grams of the hydrogen, leaves us with moles of hydrogen. So we're starting off with 4.6 moles of hydrogen. For the nitrogen, we'll do the same thing. Don't forget, H2 and N2 are both diatomic, so we multiply them by 2. So 20 grams of nitrogen gives us 0.714 moles of nitrogen. All right, so we have the moles now, and at this point it's as if we had started with moles, so we keep going. We're now going to determine the equivalence as we did before. So take the hydrogen, I turn it around. So take the nitrogen and put the 0.714 moles of nitrogen over our 1 mole. We're still using that same stoichiometric 1. Remember, what we're doing here really is comparing what we have. Think of it as what we have on the numerator to what we need. That's a good way of thinking about it. And we have a mole equivalent of 0.714. Mole equivalent is an old way I used to say it. You might see that cropping up in some of the later videos. For the hydrogen, we take our 4.96 moles divided by 3, and we end up with 1.65 equivalents. So notice that even though we had fewer grams, we had less hydrogen than nitrogen, it turned out now that the nitrogen was the one that was limiting because the number of equivalents was smaller than the number of equivalents for hydrogen. All right. I think you're ready to try it on your own now. So what I'm going to do is pause the video in a moment and then give you the chance to solve this on your own. When you get finished solving it, come back and see how you did. And we're back, so let's take a look. For this reaction now, we have 84.9 grams of iron 2 sulfide. I hope you remember that name. Multiply by 1 mole of iron 2 sulfide over the molar mass. Of course, the grams cancel, leaves us with moles of iron 2 sulfide, and with 0.966 moles of iron 2 sulfide. For the oxygen, we have 64.9 grams of oxygen. Again, oxygen is diatomic, so 32 grams per mole. Cancel out the grams, and that leaves us with 2.03 moles of oxygen. All right, we're not quite done yet. As you recall, we have to determine the equivalence. So for the iron 2 sulfide, divide the 0.966 by the 4 moles. Here's the 4 moles in the balanced chemical equation to get 0.242 equivalents of the iron 2 sulfide. For the oxygen now, we have 7 moles. 7 moles in our balanced chemical equation. So 2.03 divided by 7 is 0.290. But obviously I knew that, so I gave you a lot more oxygen than you might need, because at this point now we identify the fewer number of equivalents that the iron 2 sulfide is the limiting reactant. All right, now you should be ready to move on to the next video. In the next video, we're going to pick up where we are leaving off here, and we're going to take the amount of the excess reactant, we're going to take the amount of the limiting reactant that we've determined, and we're going to use that to calculate both the amount of excess reactant remaining and the amount of product that's formed. Both depend on how much limiting reactant there is.